Hello students, in today's class we'll derive three important equations. The first one is derivation of lens maker's formula, and second the expression for effective focal length of a combination of two thin lenses in contact, and the last one is expression for refractive index of a prism in terms of angle of prism and angle of minimum deviation. Let's study refraction through a thin lenses. Before going to understand the refraction by thin lenses, let us understand what is this lens. A lens is an optical medium bounded by two curved surfaces or by one curved surface and one plane surface. The first one is convex lens, a lens which converges the parallel beam of light passing through it is called converging or convex lens. A convex lens is thicker in the middle than at the edges. Next is concave lens, a lens which diverges a parallel beam of light passing through it is called a diverging lens or concave lens. A concave lens is thinner in the middle than at the edges. Let's understand some important terms which we need to understand while deriving some equation. The first one is principal axis of a lens. Principal axis of a lens is the line passing through the center of the curvature at the lens surface. Next is thin lenses. A thin lens is a one whose thickness is negligible compared to the radius of the curvature of the lens faces. The next is optical center. Optical center of a lens is a fixed point on the principal axis of the lens such that all ray passes through the point within the lens will have the emergent rays parallel to their corresponding incident rays. The next is focal length. The distance of the principal focus from the optic center is called focal length of the lens. The focal length is positive for convex lens and negative for concave lens. Let's understand principal focus. When a narrow parallel beam of light is incident on a lens close and parallel to the principal axis, the beam after refraction through the lens converges in the case of convex lens or appears to be diverges from in the case of concave lens to the fixed point on a principal axis of the lens. This fixed point is called principal focus of the lens. Now let's derive the lens maker's formula. This is a very important question for 5 marks. It's asked in the question like derive the expression for focal length of a thin lenses in terms of n, r1 and r2, or simply they'll ask derive the lens maker's formula. Okay, now let's start. Consider a thin lens. As you can see in the figure, thin lens, that is a convex lens of a focal length f of a refractive index n2, which is surrounded by a medium of refractive index n1 such that n2 is greater than n1. Let r1 and r2 be the radii of curvature of the surface a, b, c and ADC. O is the object point on the principal axis at a distance u from the optic center. A ray incident along OB proceeds undeviatedly. As you can see in the figure, another ray OP incident at P after refraction through the lens emerges along the QI. Refraction through a single spherical surface is given by minus of refractive index of the object space divided by object distance plus refractive index of image space by image distance, which is equal to refractive index of image space minus refractive index of object space by radius of curvature. which we have derived in our previous class. That is nothing but minus n1 by u plus n2 by v is equal to n2 minus n1 by r. Now, let us consider the refraction at the surface ABC in the diagram. In the absence of the second surface ADC, the refracted ray from a real image I dash at a distance V dash. So, from refraction at this surface, we can write it from the refraction at a single spherical surface equation, that is minus n1 by u plus n2 by v dash is equal to n2 minus n1 by r1. So we consider this as equation 2, as the equation 1 is the refraction through a single spherical surface. Okay. Next, we'll consider refraction at the surface ADC. For refraction at this surface, the image I dash acts as a virtual object forming a real image I at a distance V. For refraction at this surface, we can write it that minus n2 by v dash plus n1 by v is equal to n1 minus n2 by r2. This is also from the equation, that is equation number 1. Now we'll rewrite this equation like minus n2 by v dash plus n1 by v is equal to minus n2 minus n1 by r2. We consider this equation as 3. Adding equation 2 and 3, we'll write it as minus n1 by u plus n1 by v is equal to n2 minus n1 by r1 minus n2 minus n1 by r2. Now, next we'll write it again. n1 by n1 minus 1 by u plus 1 by v is equal to n2 minus n1 in the bracket 1 by r1 minus 1 by r2. Next, we'll reduce it like minus 1 by u plus 1 by v is equal to n2 minus n1 by n1 in the brackets 1 by r1 minus 1 by r2. So now from lens formula 1 by f is equal to minus 1 by u plus 1 by v. So we get it as 1 by f is equal to in the bracket n2 by n1 minus 1 into 1 by r1 minus 1 by r2. So this is known as lens maker's formula. Let's understand what is power of lens. The power of a lens is defined as the reciprocal of its focal length. The power of a lens denotes the power of converge in the case of convex lens or the power of divergence in the case of concave lens. The power of lens is a function of n1, r1 and r2 so that it is a characteristics of the lens. The power of a lens is expressed in terms of a unit called diopter. The power of lens in diopter is given by the reciprocal of its focal length in meters. Let's move on to another important derivation, that is effective focal length of a combination of two thin lenses in contact. This is also asked many times as per the examination is concerned, that is derive the expression for effective focal length of combination of two thin lenses in contact. So an equivalent lenses is that a single lens which produces the same effect as that of the combined effect of combination of lenses. So from figure, consider two thin lenses, that is convex lenses L1 and L2 of a focal length f1 and f2 placed in contact. We consider O is an point object on a principal axis at a distance u from the combination. In the absence of lens L2, I dash is the real image of O at a distance V dash from the combination. Now for refraction through L1, we can write it as minus 1 by U plus 1 by V dash is equal to 1 by F1. We consider this equation as 1. For refraction through L2, that is lens 2, I dash acts as a virtual object and I will be the final real image at a distance V from the combination. Therefore, we can write it as minus 1 by V dash plus 1 by V is equal to 1 by F2. So we consider this as equation 2. Now, adding equation 1 and 2, we write it as minus 1 by u plus 1 by v is equal to 1 by f1 plus 1 by f2. Since minus 1 by u plus 1 by v is equal to 1 by f, where f is the focal length of the equivalent lenses, the equation becomes 1 by f is equal to 1 by f1 plus 1 by f2. This is the required equation. Further, we'll study refraction through a prism. What is this prism? Prism is a transparent medium bounded by two intersecting plane faces, EDGF and JHGF. As shown in the figure, the faces are well polished and are known as refracting faces of the prism. The angle between the faces is called the angle of the prism. The line of intersection GF of the face is called the refracting edge of the prism. Any section that is ABC of the prism by a plane perpendicular to the refracting edge of the prism is called principal section of the prism. The prism also bounded by third face DHJE called the base of the prism. In the case of principal section, ABC is a straight line, while considering refraction through a prism or a ray of light is assumed to be in the principal section. Let's understand dispersion through a prism. Newton discovered that a narrow beam of sunlight incident on one face of a prism emerged out of the other consistence of 7 prominent colors obtained on the screen. The 7 colors are in the order of violet, indigo, blue, green, yellow, orange, and red. That is called as whipjaw. This phenomenon of separating or splitting of white light into constituent colors is called dispersion. Any medium which brings about dispersion is called dispersive medium. White light contains 7 colors. When it enters prism, refraction takes place. Since rays of different wavelengths, that is colors, travel with different velocities, refractive index is different for different colors. Hence, when a ray of composite light passes through a prism, different colors are deviated to different extent. Therefore, the incident ray is split up into its constituent wavelengths on passing through prism. Now, let's derive the expression n is equal to sine A plus D by 2 upon sine A by 2. Or they'll ask, derive expression for refractive index of a prism in terms of angle of the prism and angle of minimum deviation. So, in the figure, let x, y, z be the cross section of a prism of a refractive index n and a reflecting angle A. A ray incident along PQ on a face XY after refraction emerges along RS. As you can see in the figure, let R1 and R2 be the angle of incidence and angle of refraction respectively at the surface XY. Let R2 and I2 be the angle of incidence and angle of emergence respectively at the surface XZ. The deviation produced by the face XY can be written as d1 is equal to I1 minus R1. Next, the deviation produced by the face XZ can be written as d2 is equal to I2 minus R2. Now we'll write the net deviation produced by the prism for the ray of light is d is equal to d1 plus d2, that is I1 minus R1 plus I2 minus R2, or simply we can write it as d is equal to I1 plus I2 minus R1 plus R2. We consider this as equation 1. Now from triangle QNR in the figure, R1 plus R2 plus triangle QNR will be 180 degree. We consider this as equation 2. In quadrilateral, XQNR is A plus angle QNR is equal to 180 degree. Now this also we consider as equation 3. From equation 2 and 3, A is equal to R1 plus R2, that is equation 4. Therefore, from equation 1 becomes D is equal to I1 plus I2 minus A. We write this equation as 5. From equation 5, we find that for a given value of deviation D, there are two values of angle of incidence, namely I1 and I2. Now, from the graph showing the variation of angle of deviation with the angle of incidence is at the minimum deviation position of the prism, incident ray and the emergent ray are symmetric to each other. Therefore, I1, I2 is equal to I and R1, R2 is equal to R, and the minimum deviation D, the small d, let small d is equal to the capital D angle of minimum deviation. So therefore, equation 4 is A is equal to R1 plus R2 becomes A is equal to 2R, or R can be written as R is equal to A by 2. Therefore, equation 5 also becomes D is equal to 2I minus A. That is 2I is equal to A plus D, or simply I is equal to A plus D by 2. Now, refractive index of the material of the prism N is equal to sin I by sin R. So, substituting the value of I and R, we can write the equation as N equal to sin A plus D by 2 totally divided by sin A by 2. So this is the equation which we wanted to derive. In the next class, we'll study about optical instruments. Thank you.